We discussed till the third one in the last class. So here in this figure, we have to find angle BDC. BDC. This angle BDC. So you can see that angle BDC is subtended by arc BC. Arc BC subtends angle BDC at the point D on the circumference of the circle. The same arc BC subtends angle BOC at the center O. We have understood in the last class that it's very easy to make out the angles subtended by the same arc at the center and on the circumference. The name of the angles. See, one is angle BDC, the other is angle BOC. So you can see here arc BC subtends an angle at the point D on the circumference. The same arc BC excuse me, subtends angle BOC at the center O. And we know that by the theorem, the angle at the center is double the angle on the circumference made by the same arc. Okay, so we have angle BOC equals twice angle BDC. BDC is this angle. BOC is this angle. You can see that this angle is made at the center by arc BC because the name of the angle is BOC. So it is made by arc BC. The name of this angle is BDC. So it's made by the same arc BC at the point D on the circumference. So the theorem connects such two angles. The angle at the center is double the angle on the circumference. Now, how much is this one? A linear pair 180 minus 104. This angle is not given, but you can find linear pair. So this is 76. So 76 is equal to twice angle BDC. Substitute in the correct places. Angle BOC is 76 is equal to twice BDC. So BDC is equal to 76 by 2. 38 degrees. Now in this figure is OABC a cyclic quadrilateral? Is OABC a cyclic quadrilateral?
No, ma'am.
No,
No,
it's
miss.
not a cyclic quadrilateral. Correct. It is not a cyclic quadrilateral because the point O is the center of the circle. It does not lie on the circumference. A quadrilateral is said to be cyclic if all its vertices lie on the circumference of a circle. If all the vertices of the quadrilateral lie on the circumference of a circle, then it is cyclic. So here OABC is a quadrilateral, but not a cyclic quadrilateral. Okay. So here this angle is given. AOC is 130 degrees. We need to find OAC, this angle, and ABC, this angle, ABC and OAC, this angle. All right. So what is the name of this angle? How do you name this angle? The one which measures 130 degrees. How do you name it? What do you call that angle? Like, is it ABC, BCA? What's the name of that angle?
Angle AOC.
Yeah, it is angle AOC. So it is made by which arc?
Arc AC.
AC, miss.
AC, ma'am.
Arc AC. So this is the arc. AC is the arc. AC is the arc that subtends angle AOC at the center. Excuse me. Yeah. Now to find this angle, you can see that this is the arc. AC is the arc. AC is the arc which subtends AOC at the center. But when, see, we have to find angle ABC, but B is a point on the arc itself. So you cannot use the theorem here. The theorem that the angle at the center is, twice the angle on the circumference. That cannot be used here because this point B is on the same arc AC. So what you do, you find the reflex of this angle. What's the reflex of angle AOC? See, angle AOC is 130 degrees. Reflex of angle AOC is equal to how much? How do we find reflex of angle AOC? Is this one. 360 minus 130. 360 minus 130, which is 230 degrees. So the measure of this angle is 230 degrees. 230. Now the major arc AC, the major arc AC subtends angle AOC, this one, the reflex of angle AOC at the center. See, I told you the angle will go in the direction of the arc. So if you're talking about this arc, the major arc AC, then this is the angle subtended by it at the center. The introduction class, I repeated this many a times. The major arc AC subtends reflex angle AOC at the center. Reflex angle AOC at the center. Now take a point, not on this arc, on the remaining part of the circle. So this is the remaining part of the circle. This is the remaining part of the circle. And B is a point on the remaining part of the circle. The same major arc AC subtends ABC at the point B on the remaining part of the circle. Remaining part of the circle meaning not on that arc itself. Not on the major, that point B should not be on the major arc itself. It should be on the minor arc, the remaining part of the circle. Once again, this is the major arc. The major arc subtends reflex angle AOC at the center. Now we have to take a point on the minor arc. B is that point on the minor arc. The same arc AC, the major arc AC, subtends angle ABC. AOC, ABC, same arc AC. Same arc AC subtends ABC at the point B on the remaining part of the circle. So the relation by the theorem is between this angle and this angle. Reflex of angle AOC is equal to twice of angle ABC. Reflex of angle AOC is subtended by the major arc AC at the point O, that is at the center of the circle. The same major arc AC subtends angle ABC at the point B on the remaining part, that is on the B is a point of the minor arc. So on the remaining part of the circle. So this is the relation between the two angles by the theorem. So substitute the values in the right places. Reflex of angle AOC is known, 230 is equal to twice angle ABC. So angle ABC is equal to 230 by 2, which is 115 degrees. So this angle ABC is 115 degrees. Next, we have to find this angle OAC. OAC. So join OAC. So this angle. See your children. OAC. 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 So this angle. OAC. This one. We have to join AC in order to mark angle OAC. OAC. This angle. We have to find. Now, triangle OAC is isosceles because OA radius, OC radius. So it's isosceles. So the base angles are equal. This angle is equal to this angle. So 180 minus 130, 50 degrees, 50 by 2, 25. This is 25, this is 25. So angle OAC is equal to 25 degrees. Excuse me. Yeah. So find X and Y here. So we know that the measure of this angle is 55 degrees. Let's name this angle. So this angle is called angle ABC or CBA. CBA or ABC. So angle in the figure, we see that angle ABC is equal to 55 degrees. So clearly ABC is made by the arc AC. ABC, this angle is made by the arc AC. Arc AC subtends angle ABC at the point B on the circle. Arc AC. See, the point B is not on the arc itself. Arc AC. There's a point B on the circle. Subtends angle ABC at the point B on the circle. ABC is 55 degrees. Now, how do you name this angle? AOC. AOC. How do you name this angle? AOC. ABC, AOC. See, when you know the measure of an angle, try to name the angle. Then we get an idea. So since we know an angle here in the figure is 55 degrees, we try to name it. It's called ABC. ABC. So the same angle, the same arc AC subtends angle AOC at the point O, which is the center of the circle. So the relation between these two angles is angle AOC is equal to twice angle ABC. The angle in the center made by the arc AC is double the angle made by the same arc AC at the point B on the remaining part of the circle. So angle AOC is equal to 2 into 55, 110 degrees. So the angle of the center X is 110. X is 110. Next, we have to find Y. Now, OADC is not cyclic. OADC is a quadrilateral, but not cyclic. But BADC is cyclic. BADC. BADC is cyclic. BADC. Cyclic. So in a cyclic quadrilateral, opposite angles are supplementary. So B and D are opposite angles. Opposite angles. A and C are opposite angles. So 55 plus Y is equal to 180. Opposite angles are supplementary. Don't see this line segment. Don't see this one. Don't see all this. Just see that cyclic quadrilateral BADC with no line segments going in the middle. So this is 55, this is Y. Y plus 55 is equal to 180. In a cyclic quadrilateral, opposite angles are supplementary. So y is equal to 180 minus 55, which is 125. Now, if you want to use a theorem, if you want to use a theorem, angle at the center is double the angle on the circumference. Then this angle y is called angle ADC. It's called angle ADC. See, we have answered both. We found x and y. X we found using 55 degrees and meaning using this angle and the theorem. Angle at the center is double the angle on the circumference. And we found y using the property of a cyclic quadrilateral. Opposite angles are supplementary. We are done. We have answered x and y. You can also do y like this. Y, this angle is subtended by the major arc AC. The major arc AC subtends angle ADC. Major arc AC. The point D is on the remaining part of the circle. It's not on the major arc. It's on the remaining part of the circle. So the major arc AC subtends angle ADC at the point D on the remaining part of the circle. The same arc, the same major arc AC makes angle AOC at the center. See here, AC, the major arc AC, and the angle is AOC at the center. AOC, reflex of angle AOC. The major arc AC subtends reflex of angle AOC at the center. The same arc AC subtends angle ADC, AOC, ADC, made by the same arc AC at the center O and on the remaining part of the circle at the point D. To identify the angle, go in the direction of the arc. So see, from here to here, this is the arc, no? See, it starts here. This and it starts here, the arc, this is the major arc, it ends here. So how do we understand the angle made at the center? I said join the ends of the arc to the center. So join A to O, C to O, the ends of the arc to the center. Join the ends of the arc to the center. So when you join like this, now you will say there's an angle here. No, we have to go in the direction of the arc. The arc is like this. So the angle is also found in the same direction. This is the angle we are talking about, which is reflex of angle AOC. So the theorem is between this angle and this angle. Reflex of angle AOC, which is made by the major arc AC at the center, is equal to twice angle ADC, which is made by the same major arc AC at the point D on the remaining part of the circle. D should not be a point on the major arc itself. It's on the minor arc AC. And to identify that angle, the same way, you should join the ends of the arc to that point D. Join the ends of the arc to that point D. So this is the angle. So reflex of AOC. X is 110, right? We found X 110. This one is 110. So the reflex angle AOC is 110. So reflex of angle AOC is 360 minus 110, 250 degrees. 250. Write it under reflex of AOC. This is the result by the theorem. So below reflex of AOC, write 250 is equal to twice angle ADC, which is Y. So ADC, angle ADC is equal to 250 by 2. 250 by 2. Y is equal to 125 degrees. So we can also find Y like this. Yeah, you can take a screenshot because I don't think I would have worked it both the ways. Yeah, cyclic work. Yeah. You can just take a screenshot so that you can work this Y in two ways. Next one. So here we have to find BAD. So since it's a cyclic quadrilateral, opposite angle is supplementary. So don't see this line. Don't see the diagonal BD going in the middle. We have to find BAD, this angle. In a cyclic quadrilateral, opposite angles are supplementary. So this is 80 degrees. Then we have to find ADB. ADB is this angle. ADB is this angle. So since we know this is 80, so in this triangle, using angle sum property, you can find ADB. So first we find this using the property in a cyclic quadrilateral, opposite angles are supplementary. Then to find this angle sum property in a triangle. DAC. DAC, this one. Excuse me, children. I'll just have some water and come back. Thank you. Yeah, children. So we have to find DAC. DAC is this angle, DAC. Now, since these two lines are parallel, this is the transversal. Co-interior angles are supplementary. So this angle will be 70 degrees. We'll see that again. See here, parallel lines, transversal. Co-interior angles are supplementary. So this is 110, no? So this angle will be 70. This full angle is 70. Parallel lines, transversal. This angle plus this angle is equal to 180. This angle plus this angle is also 180. Co-interior angles are supplementary. Okay. Now we have to find this angle DAC. Let's just call that X. We got this is 70. In a cyclic quadrilateral, opposite angles are supplementary. So 70, that is angle angle C plus angle A is equal to 180. Angle C plus angle, whole of angle C. The whole of angle C plus the whole of angle A is equal to 180. Because ABCD is cyclic. Opposite angles are supplementary. So what is the whole of angle C? 70 degrees plus the whole of angle A is X plus 50 is equal to 180. So X is equal to 60 degrees, which means DAC is 60 degrees. DAC is 60. First find this angle using the property of parallel lines intersected by a transversal. Co-interior angles are supplementary, so this is 70. Now let's just mark this as X. In a cyclic quadrilateral, opposite angles are supplementary. So 70 plus X plus 50. X plus 50 is one angle is equal to 180. So like that you can find X, which is angle DAC. Next, DCB. DCB. Oh, that we already found. Okay, DCB we already found. We had to find it to find DAC. Or okay, so I didn't notice it. Okay, fine. Supposing all right. Supposing we have to find, I didn't notice that. Like, so you can also do it in a different way without finding DCB. So then what we can do is you can use in a cyclic quadrilateral, opposite angles are supplementary. So this is 110, no? So this will be 70. Now you can use co-interior angles as supplementary. You can call this X. Now use co-interior angles as supplementary. See, since we have to also find DCB, that's the second subdivision. If sometimes you have to answer the second, sometimes it depends on the information. So here we have information, to find this in a different way. Not always, sometimes, or rarely, the subdivisions may not be in the right order. You may have to find the second one to find the first one. That may happen rarely. But in this case, we can answer it in the same order. We can find DAC and then find DCB. So cyclic quadrilateral, this is 110. Opposite angle is supplementary. So this is 70. Now parallel lines, transversal. Co-interior angles are supplementary. So this angle plus this angle is 180. So call this X. So X plus 50 plus 70 is equal to 180. So X is equal to 60 degrees. So X is 60. Now we can find DCB. This one. This you can find using opposite angle supplementary, or you can use co-interior angle supplementary. Anything. Opposite angle supplementary, or you can use co-interior angle supplementary. Anything. Okay, so find BCD. BCD, this full angle. So this angle is called BAC. And this angle is called BDC. This angle is called angle BAC. This angle is called angle BDC. BDC. Now you can see from the name that both the angles are made by the same arc BC. The arc BC is here. And the points A and D are not on the arc itself. So this BC, all of you will agree, is a minor arc. The points A and D are on the major arc. And both the points A and D are on the circumference of the circle. So here we use the theorem that angles in the same segment of a circle are equal. Angles in the same segment of a circle are equal, because with respect to this chord, a chord is a line segment. I'm just extending to show you better. So this is the chord. So don't see this one. So this is the major segment. This is the major segment. And both the angles are in the major segment. Both angles BAC and BDC are in the major segment, are formed on the circumference of the major segment. So we say angles in the same segment of a circle are equal. This is angle BAC. This is angle BDC. BAC, BDC. Angles made by the same arc BC at the points A and D on the circumference of the circle. So by the theorem, angles in the same segment of a circle are equal. Since this is 40, this is also 40. Now we can find this angle using angle sum property in a triangle. In triangle BDC, in this triangle, one angle is 40 degrees. This angle is 80 degrees. So you can find the third angle using angle sum property. So using this 40, we find this one. Then in this triangle, by using angle sum property, you know two angles. So you can find the third one using the angle sum property. Okay, so here we have to find PRB. PRB. So you can see PAB, PRB. PAB made by arc PB. PAB made by arc PB at A. Same arc PB. PRB at R. Angles in the same segment of a circle are equal. So this one is 35 degrees. PAB, PRB. So this is 35. Next, we need to find PBR. PBR. That means you should join. You need to join this. PBR. PBR. So PBR, this angle. This angle. Yeah. Without looking at the slides, can anyone tell me? PBR, and then we have to find BPR. BPR, this angle. Can we see a diameter here? Diameter. Children, can we identify the diameter in the figure?
Yes, ma'am.
Yeah. Yeah, which is the diameter? Name the diameter.
AB is the diameter.
AB is the diameter. AB is the diameter. Now, are the ends of the diameter joined to any point on the circumference? Are the ends of the diameter joined to any point on the circumference of the circle?
Yes, ma'am.
Yes. So which is that point on the circumference to which the points A and B are joined?
From point A to point B, ma'am.
No, A and B are the ends of the diameter. You should tell me another point on the circle to which A and B are joined.
Ma'am, P and R.
Not R, only P. Prenu, right?
Yes, ma'am.
Yeah, P. So you can see here, there's a point P on the circle. A to P, B to P. So this angle is 90 degrees. No, I was only asking you to, so that we can identify the angle in the semicircle. Angle in a semicircle is a right angle, is a theorem. We saw this in the last class. Angle in a semicircle is a right angle. How do you identify that? Where is the right angle formed? See, we had to join PB because we have to find angle PBR. Okay. Now, where is that right angle formed? Okay, AB is the diameter. If there's the diameter, then you can use this theorem. Angle in a semicircle is a right angle. Not that in every wherever there's a diameter, you will have to use this theorem. Not that. This theorem can be used only if you know the diameter of the circle. And angle in a semicircle, angle in a semicircle is a right angle, can be used only if in the figure, a diameter is given. Otherwise, we cannot use it. Like the RHS conference criterion. Only if the two triangles are right triangles, you can use it. But not that if the two triangles are right triangles, you have to use RHS. Not that. You can use even SSS depending on the information given. You can use SAS. You can use any other conference criterion. But to use RHS, the two triangles have to be right. You cannot use RHS to two triangles which are not right triangles. In the same way, angle in a semicircle is the right angle. This theorem can be used only if in the figure you are able to identify the diameter. You are able to identify a line segment as the diameter. Otherwise, you cannot use it. If no diameter is known, then we cannot use the theorem. So here we know AB is the diameter because it passes through O. And sorry, and O default is the center of the circle. It's also given here. Okay, so P is the point on the circumference. A is joined to P. P is joined to P. So the angle is formed here. See, APB. See, APB. APB. And this is the semicircle. This is the semicircle. This is the semicircle. A and B are the ends of the semicircle. And you can see they're joined to this point P on the circumference. This angle is 90 degrees. Angle in a semicircle, but angle in a semicircle is a right angle. They're talking about this semicircle. Angle in a semicircle. Angle in a semicircle is a right angle. They're talking about this semicircle. This is a semicircle. Now the angle in the semicircle, this angle, is a right angle. So how do we identify that angle? So you should identify the diameter. That's the first step. Identify the diameter. Identify a point on the circumference of the circle. Join the ends of the diameter to that point. Join A to P, B to P. Now an angle is formed, APB. When you do this, an angle is formed on the circumference. Angle APB is formed on the circumference. That angle is 90 degrees. Not some angle. See now, supposing we don't join, simply because there's a diameter here and there's some angle here, this is not 90 degrees. Not like that. It's not that, okay, there's a diameter here and some angle is there on the circumference, so this is 90. It's not like that. Diameter, ends of the diameter, point P on the circumference, join A to P, B to P. When you do this, you can see an angle formed here. Angle APB. This is 90 degrees. So this is 90. So that means this is also 90. This one, this is also 90. So we had to find this angle, no? PBR, this angle. This angle. We have to find this angle PBR. So exterior angle property in a triangle. Exterior angle property. Exterior angle in a triangle is equal to the sum of the two interior opposite angles. So this angle is equal to 90 plus 25. First, we had to find PRB. PRB. This one. PAB, PRB. So 35 degrees. So this was easy. Or direct. Not, instead of saying easy, that was direct. PAB, PRB. Reason is angles in the same segment of a circle are equal. Next, PBR. PBR. This angle, PBR. To find this angle in a semicircle is a right angle. This is 90. So linear pair, this is also 90. Now this is to this triangle PBQ. This is an exterior angle because the side QB is produced. So exterior angle is formed. This angle is equal to, leave this angle plus this angle. So this is equal to 115 degrees. So we found PBR. Next we have to find BPR. BPR, this angle. This angle. So this one angle some property. We just found this is 115. And we already know this angle is 35. We found it earlier, 35. So in this triangle, this angle we found here 115. And this angle also we have to find here 35. So using angle sum property, you can find BPR. 115 plus 35, 150, 180 minus 150, 30. So this one is using the property of a cyclic quadrilateral. Opposite angles are supplementary. So you'll have to construct two equations and solve the two equations. Angle A plus angle C is equal to 180. Angle B plus angle D is 180. So 180. So you'll get 2x plus 2y is equal to plus 4 and minus 4 gets cancelled is equal to 180. Dividing by 2 throughout. You get 2x plus 2y is equal to 180. Dividing by 2 throughout. 2x by 2, 2y by 2, 180 by 2. So that way you get x plus y is equal to 90. Then angle B plus D is angle B plus angle D is 180. Angle B plus angle D is equal to 180. So this gives you the equation x plus 5y is equal to 165. So to solve the two equations, write them one below the other. Write the equations one below the other. Now we can cancel out x and x, but they have the same sign. X plus x is 2x. So change the signs throughout. See, if it was already minus x, you don't have to change the signs. You can directly cancel. If it was, see, changing the signs throughout is only an option. When you have two equations, you can add them or subtract them. Meaning you can change the signs of the second equation, or you don't have to change the signs of the second equation. When you don't change the signs, you're adding the two equations. When you change the signs, you're subtracting the two equations. You can do anything. So when we change the signs, we are subtracting. Not that you have to always subtract. You can even add. But the situation will demand one particular thing. Now this situation demands subtraction. It's not a choice. Okay, let me add. Okay, let me subtract. No, it's not that. Sometimes, sorry. So sometimes you can do both, but not always. So that choice is not open always. Now here you have to subtract the two equations. Why we have to subtract? Why should we change the signs? Is because only if you change, see the lines which you see here, no, these are the changed signs, children. This you don't have to write it like this. You please do it here, okay? So like plus becomes minus, and this plus becomes minus. So then what happens? Plus x minus x gets cancelled. So in order to cancel, you have to change the signs. If you don't change the signs, what will happen? You will get x plus x 2x, y plus 5y 6y is equal to whatever, 155, no, 255. So that's not going to help you. So when you change the signs, plus x as minus x, plus 5y as minus 5y, plus 165 as minus 165. And now when you solve the two equations, x and minus x is 0. Plus x minus x will get cancelled. Plus y minus 5y. Take the changed signs. Forget the original signs. Take the new signs. Plus y minus 5y minus 4y. Plus 90 minus 165 minus 75. So now see, because we eliminated y. Y got sorry. Because we eliminated x. So we are able to find the value of y. Now after getting y, substitute the value of y in one of the two equations. So x plus y is equal to 90. Put the value of y here and find the value of x. You can substitute anything, children. You can also substitute this one. Anything you can substitute. Meaning you can substitute 18.75 or 75 by 4, anything. Okay. That's about this presentation. Okay. So this presentation is about exercise 10.4 NCRT. Visible to all children?
Yes, ma'am.
Yeah. Okay. So a circular park of radius 20 meters is situated in a colony. 3 boys, Ankur, Syed and David, are sitting at equal distance on its boundary, each having a toy telephone in his hands to talk to each other. Find the length of the string of each phone. Circular park. Circular park. 3 boys, Ankur, Syed, A, S and D. Okay, 3 boys, A, S, D, are sitting at equal distance on the boundary. Equal distances. So that means when you mark the points A, S and D, the length of the arc AS is equal to the length of the arc SD is equal to the length of the arc AD. Like we say, 3 sides are equal. No, here the 3 arcs are equal in length because the boys are sitting at equal distance on its boundary. The boys are sitting at equal distance on the boundary. Like supposing the circumference of the circle, for example, is 30, then the length of the arc AS is 10, the length of the arc SD is 10, and the length of the arc AD is 10. So 10, 10, 10, 30. length of arc AS is equal to length of arc SD is equal to length of arc AD. And they're having a toy telephone in their hands to talk to each other. Now we need to find the length of the string of each phone. Now the string will not be slack. The string, the string will not be slack, like it will not be hanging loosely. So when they hold it, so A is here, S is here. The string between A and S will be taut like this. It will be like fully stretched. Otherwise, you can't find. No, if they're holding it loose, how will you find? So the string between A and S. This is the string between A and S, and it's tight. There is no slack. This is the string between S and D, and this is the string between A and D. This is the string, the telephone string between A and S. This is between S and D. This is between A and D. Now, there's a theorem that says that equal arcs contain equal chords. If arcs are equal in length, then their corresponding chords are equal. If arcs are equal in length, their corresponding chords are also equal. So this is the arc. This is its corresponding chord. One second. Okay, so this is arc AS. This is chord AS. This is arc SD. This is chord SD. This is arc AD. This is chord AD. Equal arcs contain equal chords. Now these three arcs are equal, so their respective chords are also equal, which makes ASD an equilateral triangle. Now the idea to find the answer is very simple. Divide the triangle into three smaller triangles. This is center of the circle. This is the center of the circle. Join the vertices of the triangle, that is A to O, S to O, D to O. Join the three vertices A, S, and D to the center O. So like this, we divide the triangle ASD into three smaller triangles. Triangle AOS, triangle SOD, triangle AOD. We have divided the whole triangle into three smaller triangles. So the idea is the area of the whole triangle ASD, the area of the whole triangle ASD is equal to the area of the three small triangles, the sum of the areas of the three small triangles. That's the idea used here. Yeah. So I'm pausing to manage my throat, children. So the triangle ASD is equilateral. ASD is equilateral. And the area of the triangle is √3/4 into A square. Divide the triangle into three smaller triangles, AOS, SOD, AOD. Now, area of triangle AOS plus area of triangle SOD plus area of triangle AOD is equal to the area of the whole triangle ASD. But these three triangles, they're identical. So they'll have the same area. Why they're identical? Because this is the radius 20. This is the radius 20. This is the side of the equilateral triangle A. Radius 20, side A. radius 20, side A. So you can see each of the triangles have the same sides 20, 20 and A. 20, 20A. The three triangles, the sides of the three triangles are 20, 20 and A. So then our equation is still simpler. Area of the triangle area of triangle ASD, the whole triangle. Area of triangle ASD is equal to 3 times the area of triangle, any one triangle you can write. 3 times area of triangle SOD, any one triangle you can write. That's all. You need to find the area of the whole triangle using Heron's formula. So I want you to work that now. Please work and then we'll discuss so that when you work it, you have some idea. And then when we, talk about it together, it'll be more clear than me just talking about it. And then you have to go through. Since you know Heron's formula. Yeah, please write the question and take down this answer, children. As you write, please understand what you're writing. And then we'll discuss. Children, use the emoji, raise your hand. Aniruddhan, Swati, Hari Pranav, Prenu, Krishna Priyan, Abhishek, Nritsa, Laksha, Aragamai, Niveda, Anugraha, Sahana, Savarna, Sadhana, Bhavishya. Aniruddhan, you're telling me something, Aniruddhan?
No, ma'am.
Okay, okay. Very good, children. All right, yeah. I'm not asking you to hurry, but do it at a good pace because I want to finish at least 6, 5, and 4 today. This one, the 6, 5, and 4 of this exercise. I'll come back in 5 minutes. Please finish. Finish, children?
Yes, ma'am.
Yeah. So till here, we've already discussed why triangle ASD is equilateral. Okay. So we have to find AS, the length of the string AS, or you can find SD or AD because it's equilateral. We have to find the length of the string, which is AS or SD or AD. Now, area of these triangles are equal because they have the same sides, 20, 20 and A. So the area of these triangles are equal. So the area of the whole triangle ASD, the area of this whole triangle ASD is 3 times the area of the triangle AOD. The whole triangle, this whole triangle is made up of these 3 triangles, 1, 2, 3. Triangle 1, this is triangle 2, this is triangle 3. Area of triangle 1 plus area of triangle 2 plus area of triangle 3 is equal to the area of the triangle ASD. But 1, 2, 3, all of them have the same area because they have the same sides, 20, 20 and A. So you can write area of the whole triangle ASD is equal to 3 times the area of the triangle AOD. Excuse me. Yeah. So now the area of the whole triangle ASD we know is root 3 by 4 into A square. There's nothing to find there because the side is A. The side is A. So the area of the whole triangle ASD is root 3 by 4 into A square. Now we'll find the area of this triangle using Heron's formula, AOD using Heron's formula. So this is a semi-perimeter, 20 plus 20 plus A by 2. So 40 plus A by 2 is a semi-perimeter. Area is equal to S into S minus A into S minus B. Again, you'll get the same thing, right? Because 2 sides 20. That's why I put a whole square here. Whole square meaning the same thing, no? S minus A into S minus B. 2 sides are 20. So you'll get the same thing. So I put a whole square. Instead of writing it, I put a whole square here. Into S minus C. S minus C. The third side, A. S minus A, S minus B, S minus C. After that, common denominator, LCM. So it will become 2 into 20, 40. Here it will become 2A. LCM. This step is LCM. Then this one as it is. 40 minus 40 gets cancelled or 0. So A by 2 the whole square. And here minus 2A plus A is minus A. So 40 minus A by 2. So here A by 2 the whole square. So now all these are under the square root. So A by 2 the whole square will come out as A by 2. And in the denominator there are 2 2's. So 1 2 will come out, but it's in the denominator. So you should write it as 1 by 2. See, this step can be interpreted like this. This step, this step, we have square root of this step, square root of, we have 40 plus A into 40 minus A. Sorry. So we have 40 plus A. We have 40 minus A. Then that by 2, no? So it's like into 1 by 2 into 1 by 2. And then we have into A by 2 the whole square. It's a product, no? So you can look at everything separately. It's a product. 40 plus A and 40 minus A we have in the numerators. Sorry, we have in the numerator. 40 plus A and 40 minus A we have in the numerator. So you can see it here. Then we have that a by 2 the whole square here, a by 2 the whole square. Then we have by 2 by 2. That means into 1 by 2 into 1 by 2. So two 1 by 2s we have. So one of it will come out of the square root. And a by 2 the whole square. So a by 2 out of the square root. So in the square root, you will have only these two expressions. And now this is like a plus b into a minus b, which is a square minus b square. A plus b into a minus b, which is a square minus b square. So now this is a by 4 square root of 1600 minus a square. So this is the area of triangle AOD. Area of triangle AOD is a by 4 into square root of 1600 minus a square. Meter square because the radius is given in meters. Now write the equation. Area of the whole triangle is equal to 3 times the area of the small triangle AOD. So this one is root 3 by 4 into a square. Now this is 3 times area of triangle AOD. This is area of triangle AOD. So 3 times meaning 3 into this one. Write this equation and substitute the areas. This one is root 3 by 4 a square, the whole triangle. 3 into area of triangle AOD, this one. So what happens? 4 and 4 will get cancelled. And then this a and a square, so it will become a here. And then this root 3 and here. So 1 root 3 will be here. So that's what we have. A is equal to root 3 into root of 1600 minus a square. See here. This 3 root 3. So 1 root 3 will remain here. 4 and 4. Then a square and this one. The one a will remain. See, otherwise what you can do is you can take everything to this side. This is 3a by 4, no? This one is 3a by 4. So on the other side, it will become 4 by 3a. When you transpose, when you take it to the other side, when you bring this here, 3a by 4 will become 4 by 3a. So 4 and 4 will get cancelled. Then this one and this one. There will be 1 root 3 here. A and this one. So see, you have a by root 3. So that a by root 3 only is a is equal to root 3. We'll have a by root 3, right? A by root 3. So that's what is here. So now at this point, square on both the sides. Because you want to get rid of the square root. Yeah, so square on both the sides because you want to get rid of the square root. So squaring on both the sides, you have a square is equal to, when you square this, it becomes 3. When you square this, it becomes 1600 minus a square, meaning the square root is eliminated. The square root is gone. When you square on both the sides, the square root is eliminated. So we have 3 into 1600 minus a square. Here, when you square, you get a square. This becomes a square. Here, when you square, we get rid of the square root symbol. So a square is equal to 4800 minus 3a square. Then transpose minus 3a square on this side. So it will become 4a square. A square plus 3a square. 4a square is equal to 4800. A square is equal to 4800 divided by 4. A square is 1200. A is equal to square root of 1200. So prime factorization, do that and you will get 20 root 3. A is equal to 20 root 3. So the length of the string each boy has is 20√3 meters. So you just have to remember the idea because you know how to use Heron's formula. So the idea is to divide the whole triangle. Triangle ASD is equilateral. Divide the whole triangle into 3 smaller triangles, and you should use this equation that the area of the whole triangle ASD is equal to 3 into area of triangle AOD. This is the equation. Now area of this triangle we know √3/4 into a square. Area of this triangle you should find using Heron's formula. That's what we have worked here. This is the equation. This is the main equation. In this one, we know the area of this triangle is √3/4 into a square. Area of triangle AOD has to be calculated using Heron's formula. And that's what we have done here. Then we just have to substitute the values in the formula, simplify here, and then to get rid of the square root symbol, we square on both the sides, and that's it. Once you square on both the sides, you are able to find the value of A. Any questions, children?
No, ma'am.
Okay. No, ma'am. One of the earlier classes, I don't remember if it was the last class or sometime last week, children. We were working, a question paper. I have prepared the answers. I'll share the word file with you. I prepared for section A, B, and C. It's ready with me now. I'll share it after the class. Okay, D and E will work in the next class. Or if it is ready, if I'm able to prepare the answers, I'll share it with you on WhatsApp. I don't know if I don't send the answers for D and E by the next class, we'll do it in the class. Meaning we'll discuss the answers in the class. If I find time, I'll work the answers and I'll share it with you on WhatsApp. A, B, C, I've prepared. I'll share it now. After the class, I'll share the file. So it will not take a long time for you to check your answers with the answers I've shared. Mark your questions and we can see them in the next class. This will take some time. I think we'll do the fourth one. Okay. 5 will take some time, children. It might get too late for you. Okay. We'll do 4 and wind up the session for today. If a line intersects 2 concentric circles with center O at AB, C, and D, prove that AB is equal to CD. Concentric circles, that means they have the same center but different radii. So a line intersects 2 concentric circles. A line intersects 2 concentric circles with center O at the points A, B, C, and D. A, B, C, and D. A line intersects 2 concentric circles at the points A, B, C, and D. We need to prove that AB is equal to CD. Now, in this chapter circles, the default construction is dropping a perpendicular from the center to the chord. Now, this is a line, but AD is a chord. BC is a chord to the inner circle. AD is a chord to the outer circle. BC is a chord to the inner circle. AD is a chord to the outer circle. The whole thing is a line, but in the line there are line segments. So the segment AD is a chord to the outer circle and the segment BC is a chord to the inner circle. Now in circles, default construction is dropping a perpendicular from the center to the chord. So construction, draw OM, you can call it anything, I've called it M here, so I'm calling it M here. Draw OM perpendicular to BC or AD, it's the same line, no? You can say draw OM perpendicular to BC or AD, or you can say draw OM perpendicular to the line L. All the same. Draw OM perpendicular to L. Now, this is the construction. That's what we understood. This is a default construction, dropping a perpendicular from the center to the chord. Now, by the theorem, the perpendicular from the center to the chord bisects the chord. The perpendicular from the center to a chord bisects the chord. Now, AD is a chord to the outer circle. The chord is bisected at M because OM is the perpendicular. No, so the chord is bisected at M. So that means AM is equal to MD. The chord is AD. The chord is AD. AM is equal to MD. Then there's another chord BC to the inner circle. On that also you have this OM. We have BC. So BC chord to the inner circle. OM perpendicular. So the chord is bisected. BM is equal to MC. Subtract these two. AM minus BM. AM minus BM is AB is equal to MD minus MC is CD. So we proved that AB is equal to CD. See, you can also mark, you take a screenshot of this one. This will be better. You can call this line L and you can say draw OM perpendicular to L. So, so you can see here, BC is a chord to the inner circle and OM is perpendicular to BC. The perpendicular from the center to the chord bisects the chord. The chord is BC. The chord is bisected at M. So BM is equal to MC. In the same way, to the outer chord, AM is equal to MD. Subtract the two results. You can even write it one below the other, like how I wrote it here. Oh, sorry. You can even write them one below the other. AM is equal to MD. This is the bigger one. And below that, you can write BM is equal to MC. And subtract. AM minus BM is AB is equal to MD minus MC is CD. Hence, we prove that AB is equal to CD. Any questions, children? Got it? Okay, no response. All right, children. All right, children. So that's it for today's session. Thank you so much. Good night. You may leave the call.
Thank you, ma'am.
Thank you, children.
Thank you, ma'am.
Thank you. Good night.